This section explains the Stable Diffusion model and code implementation. Let's first look at the Stable Diffusion model overview. A diffusion model is a generative model that learns to transform a sample from noise to data by progressively denoising it. This process works by simulating a forward diffusion process, adding noise, and a reverse diffusion process, removing noise. In the case of Stable Diffusion, the model is specifically used for generating high-quality images. Time embeddings. One key feature of diffusion models is the time encoding, which tells the model at which step in the diffusion process it is. This is important because the model needs to know how much noise has been added to the image and adjust its predictions accordingly. Time embeddings are typically done using sinusoidal embeddings as a function of the time step t. The embedding function for time step t is as follows. Frec I is computed using a logarithmic scale. This gives us both sine and cosine components that allow the model to distinguish between time steps. These embeddings are crucial because the model uses them to understand the progression of the diffusion process, guiding how much noise is added or removed. U-Net. The core of the Stable Diffusion model is the U-Net architecture, which is designed to take in noisy images and predict the noise component that was added to the original image. U-Net is effective because of its skip connections, which allow information to flow from earlier layers, which capture low-level details, to later layers, which capture high-level features. Let's break down step by step. 1. Initial convolution. The first step is to process the input image X using a convolutional layer. This converts the image into feature maps, which are then processed through a series of downsampling and upsampling layers. 2. Downsampling path. The image is progressively downsampled using convolutional layers, batch normalization, ReLU activations, and max pooling. The purpose is to capture abstract features of the image while reducing the spatial dimensions. At each downsampling step, the output feature maps are saved for use in the upsampling path via skip connections. 3. Middle block. In the middle of the network, we inject the time embedding. The time embedding is projected into the same spatial dimension as the feature maps, and it is added to the feature map. This allows the model to condition its denoising process on the current time step. 4. Upsampling path. The upsampling path restores the spatial dimensions of the image using transposed convolutions, also called deconvolutions. The skip connections are concatenated with the upsampled feature maps to provide the model with both high-level and low-level features. At each upsampling step, the model learns to generate a cleaner image, slowly removing the noise. 5. Final convolution. Finally, the output of the U-Net is passed through a convolutional layer that matches the input image's shape and color channels. Diffusion process. Adding and removing noise. The diffusion model operates in 2 steps. Adding noise, forward process, and removing noise, reverse process. In the forward diffusion process, noise is progressively added to the image x0. The image at time step t is given by as follows. Alpha t controls how much of the original image is kept at each time step. Epsilon is Gaussian noise added at each step. The reverse process involves predicting the noise added at each step and removing it from the noisy image xt. The reverse process can be expressed as follows. Epsilon theta E is the predicted noise produced by the U-Net. Noise correction compensates for the noise added at each step to ensure a smooth reverse process. Sampling process, image generation. Once the model is trained, generating an image from noise involves running the reverse diffusion process. Starting from random noise, the model iterates through the time steps in reverse, predicting and removing noise at each step. This gradually leads to the generation of an image. The sampling process is as follows. 1. Start with random noise xt. 2. At each time step t, predict the noise epsilon and remove it using the reverse process formula. 3. Repeat this process until reaching t equals 0, where the model outputs the generated image. Now we implement the Stable Diffusion code. UNet class. Sinusoidal position embeddings class. Diffusion model class. Testing the Stable Diffusion model.